I said earlier that if we have a symmetrical distribution, it could be the case that a measure of location and a measure of dispersion, like the mean and the standard deviation, are all that we really need in order to mostly characterize what the distribution is like. But this is not always going to be the case. And I want to discuss two more measures that are used to characterize distributions: their skewness and their kurtosis. Okay, let's start off with skewness. Let's look at these graphs that we've seen before. Let's start off with this graph here. This is a symmetrical distribution. In this case, probably knowing something about the mean and the standard deviation will be good enough to describe it. There is, in this distribution, because it's symmetrical, no skew to the left or the right. Down here, we have a distribution which is left skewed or negative skewed. There's clearly some very, very, very small values right out here. And on this side, we've got a right or positive skewed distribution, one with some very, very high values out to the right-hand side here. So this suggests that there might be a need for a number, a measure, which captures how much skewness there is in the distribution and tells us what the direction of skewness is, whether it is to the right or the left. There are some relationships between the mode, the median, and the mean of a distribution. In a symmetrical distribution, the mode is equal to the median is equal to the mean. Skewness is about the degree and direction of asymmetry. In a right skewed distribution, the mode is less than the median and the median is less than the mean. In a left skewed distribution, the mode is greater than the median and the median is greater than the mean. The skew spreads out these three different measures of location. Intuitively, a good measure of skewness should take the value of 0 if the distribution is symmetrical. It should tell you which direction the skewness is in, whether it is to the right or the left. It should tell you what the magnitude of the skewness is, how big it is. Now, there are a number of different approaches to doing this, and I'm just going to mention one of them here, essentially. That's Carl Pearson's approach. In fact, he actually defined two different measures of skewness, but only one of them is actually terribly useful. His first measure takes the mean, subtracts the mode, and divides it by the standard deviation. But for a continuous distribution, this is probably not terribly helpful, since obviously the mode is very often not very well defined. The second measure, much more useful, is to define skewness as 3 times the mean minus the median divided by the standard deviation. And that's an approach that you will see mentioned from time to time. The other kinds of approaches to skewness I discuss in a separate something extra video. So if you're really very interested in it, you should take a little look at that. But it's really not something which is important for this course. If we have a skewed distribution, it's really rather obvious that simply just knowing the mean and the standard deviation isn't going to describe everything about it that we might want to know. However, there are circumstances in which we might want to distinguish between different types of symmetrical distribution. That means that we might be interested in a slightly different sort of measure, and that measure is called a measure of kurtosis. Consider the distributions in this plot here. In all three of these distributions, the mean is equal to 0. And in fact, the standard deviation is equal to 1. It's also the case that the skewness is equal to 0, which indicates that the distributions are symmetrical. However, they're obviously all very different from each other. So the question arises of how should we distinguish between them? That's why we need a measure of kurtosis. Let's define some terminology to denote different types of symmetrical distribution. First of all, we have the mesokurtic distribution. That's the distribution described by the black line here, somewhat sitting in the middle of the other two symmetrical distributions. This has the same kurtosis as a normal distribution. A normal distribution is a very special kind of symmetrical distribution. In fact, we will meet it over and over again in the next few weeks. We'll make quite a lot of use of it. But it's important to realise that not all symmetrical distributions are normal distributions. We're going to use this mesokurtic or normal distribution as a kind of reference point to compare other sorts of symmetrical distributions. The blue distribution here is called a leptokurtic distribution. From the Greek lepto equals narrow and kurtic means humped. So a narrow humped distribution where narrow is relative to the mesokurtic distribution, to our reference distribution. You can see that it's taller, more peaked, as it were. The red distribution here is called platykurtic. Platy for broad. It's more spread out, as it were, than our reference mesokurtic distribution. The English statistician who was known as Student, in fact a man called William Seeley Gossett, who was the head brewer of the Guinness Brewery, invented a not very amusing mnemonic. Platykurtic curves, he said, are like the platypus. They're squat with short tails. Leptokurtic curves are high with long tails, like the kangaroo, noted for lepping. Ha ha ha. It's common to see in otherwise reputable textbooks the opinion that kurtosis is about the peakness of the distribution. But this is in fact actually slightly misleading, and measures of kurtosis are most influenced not by observations in the peak, but in the shoulders and the tails of symmetrical distributions. Let's look in a little bit more detail at a comparison between a mesokurtic and leptokurtic distribution. Remember that we're treating the mesokurtic distribution as a sort of reference distribution. So how do we get from that to the leptokurtic distribution? Well, obviously we're taking observations from this area here and this area here, and we're dumping them up here, and we're also moving some of them out to the tails down here. So you can really see readily it's not just a matter of heaping them up and making the distribution more peaked, it's also a matter actually of putting more observations out in the tail. The tails are a little bit thicker than in the mesokurtic case. Now let's compare the mesokurtic and the platykurtic. So here in black we've got the mesokurtic distribution. And what are we doing? Well, we're taking, as it were, observations from up here in the peak and putting them at the side here and here. We're broadening out the width of the distribution, as it were, in this region here. and we're also taking observations from the tails and putting them there as well. So the mesocurtic distribution actually has slightly fatter tails than the platycurtic distribution. Okay, of course it is possible to come up with numerical values for kurtosis. How one actually does that I'm not going to talk about right now, but you can find out more in my Something Extra video about skewness and kurtosis. So if you're really interested in it, take a look at that, but it's really not an essential part of the course that you need to know.